Hello AP Physics 2 students, it's time for some circuits. In this video we're going to cover the basics, and the next video we're going to cover some more advanced material. Let's start with current. Current is the flow of charge. Now this is a real thing. Remember, protons and electrons exist, and so they move through the wire. So there's this conservation of charge that has to go on. They don't just vaporize when they go through, say, a clock or your iPhone. The charge is still there because they're real things. This charge flows past a point, and the delta Q, the amount of charge divided by the time, will give you the current in units of coulombs per second, or amperes, amps for short. There must be a potential difference. So if I want to shove charge through anything, say like this pen, then I have to have a higher potential on one side than the other. There has to be a potential difference. And we're always going to be talking in this class about conventional current. That's the movement of positive charge from high to low potential as we go through the device. In reality, we know it's actually in a solid that electrons move, and they would move from low to high potential. Electric potential is energy per charge. We talked about this in static electricity. Current's going to flow again through a potential difference from high to low for conventional current. So there has to be a difference. So if we have a device in the circuit that has the same potential on each side, then there won't be any current going through it. So every time an object is sitting there with no current going through it, the potential on each side is exactly the same. The current is forced through from high to low volts, like we already said. Anytime the current goes through a device, it's going to lose some of this energy, some of this electric potential. So it'll have a higher potential than on one side than the other. But there has to be conservation of energy. So the amount of potential that's supplied in a loop has to equal the potential that's consumed. We'll go into that more a little later in Kirchhoff's rules. All right, resistance. Resistance is like electric friction. It's a hindrance to the flow. It's measured in ohms. And resistance turns this electric potential energy into heat. So when the volts decrease by going through a device, if it's a resistor, it will turn that electric potential energy into heat energy. Now, we will model all sorts of things as a resistor. It could be an oven that actually produces heat. It could be a TV that's producing light and sound. It could be anything. It could be a motor, like in an electric car, that produces kinetic energy. But that electric potential energy will turn into something else when it goes through the resistor. If it's an actual resistor, then it will have a resistance as shown here. Resistivity, path length, and cross-sectional area. Now in class we generally draw this. This is a resistor with a length and cross-sectional area, but it could be a rectangle. It doesn't matter, just find the cross-sectional area. And this resistivity is a property of the material. So insulators have a really high resistivity, conductors have a really low resistivity. We have to look it up in a table or do a lab with this equation right here and find out what it is. Now, ohmic versus non-ohmic. Does the resistance of the object stay constant, or does it change in different circumstances? Generally, what we find is that nothing is truly ohmic across all possible situations. But, like a light bulb that we did in class. As we sent electricity through it, as it got hotter, the resistance went up and didn't remain constant. So that would be non-ohmic. But over the operating range that we might put a device through, it could be ohmic as long as the resistance remains the same for the conditions we're considering. Now let's talk about Ohm's law. Ohm's law is I equals delta V over R, or the way we write it usually, because we hate fractions, is delta V equals IR. But it's this potential difference or voltage that pushes the current. They're proportional. And the resistance or electric friction that is inversely proportional to the current that hinders it. And again, ohmic versus non-ohmic. All we have to do is rearrange the equation, or like we see here, I is a function of 1 over R, or I is a function of V in this graph, the current and voltage. If this turns out to be a straight line, then the slope is 1 over R from our equation. If it's not a straight line, then it's a non-ohmic device. This one being like a diode, a semiconductor. All right, power. Power is the rate at which work is done or energy is converted into something else. Electric potential energy converted into something else. Now, the standard equation for it is P equals IV. But if you use Ohm's law, you can create these other two. These two are not on the equation sheet, so you have to memorize them.
A power relates to light bulbs. The more current or voltage we have across the device, the more power it has and the brighter it will be. So like if we have more current through the bulb, it'll have more power. It's converting electrical energy into light faster, or more potential across it for the same current, and it has more power. A motor is the same way. A motor converts current and voltage into power to move something, to make it go faster or to do work. So the motor could be lifting a weight. So the electrical power supplied to the motor would be equal to the rate at which it's lifting the object, mgy over the time.
Motors can also change the kinetic energy of a car, say. So it's the power, the electrical power IV is creating kinetic energy in the car. So 1 FmV squared, the rate that is changing divided by time, is equal to the power, electrical power supplied to the motor. All right, let's look at schematics. So we don't want to draw a real picture of circuits. We want to use schematic diagrams to make them as simple as possible. So remember all of these. All right, let's make sure that we know how to connect a meter. Voltmeters, remember, measure potential difference. So they have to hook to both sides of the device. So voltmeters are always connected in parallel. So like this voltmeter right here in this figure will find or measure the potential difference for resistor 3, because we have to put it around the resistor. Ammeters measure the current that passes through the device. So if we want to measure the current, say for resistor 3, then we have to put the ammeter in series with it. So the current has to go through that ammeter and also go through resistor 3. So this ammeter right here will read the current that passes through R2 and R3, whereas this one right here, ammeter number 1, will measure the current passing through the battery and passing through resistor 1. Okay, so now how do we visualize all of this stuff? Because in mechanics, we can touch it, we can feel it, we can throw it across the room. But in circuits, we can't see the electrons or the charge moving around. So how do we visualize it? So there's a couple things we're going to do. We can color the circuits. Now, you don't have to color it in Roy G. Biv if you don't want to, but just realize that these different sections will be a different color, a different electric potential. And so there will be a different potential on either side of these resistors whenever there is current flowing through them. And current is easy to visualize with an arrow going through the circuit. So this one right here is a series circuit. So if we colored this one and put a arrow for the current, we would see that this is the high voltage side of the battery. And then the voltage drops as we go through the first resistor, and then drops some more as we go through the second, and then the third. Notice the meter, unless it has resistance, which we hope it doesn't, will not do anything to the electric potential. So an ideal meter doesn't affect the circuit at all, even though in reality it probably does. And then the voltage drops, and then the battery pumps the voltage back up. So it drops across all of these consumers of the energy, but is pumped back up by our EMF or battery. So we only have one current going through a series because there's only one pathway. Okay, here's a parallel. What will this one look like when we draw arrows and we color the circuit? Well, in this one, we can see that this is the high end of the battery. And so everything from here to here is connected to the high end of the battery. So that will all be high volts. And these sides of the resistors are all connected to the low end of the battery. So they'll all have low volts. So actually, parallel is pretty simple. They have the same exact potential difference across them. And they have different currents, though. So the current that passes through ammeter 3 and the battery will split into two separate pathways. So we have current 1 going through resistor 1 and current 2 going through resistor 2. If we have a combination circuit like this, then it gets a little more complicated, but the rules that we just learned for series and parallel still are in play. So if we color this circuit and draw the arrows, you'll see that there is a current that comes out of the battery on the left side, passes through resistor 1. It splits into two parts. Current 3 goes through resistor 4 up here that I have, and then current 2 that I've drawn goes through resistor 2 and 3 and this ammeter. So this ammeter reads the current for these two. Ammeter 3 reads the current for resistor 4. And then ammeter 4 reads the combination of these two back, and hey, those two have to be the same, right? Because this one's going into the battery, this one's coming out of the battery. Notice that resistor 2 and 4 are not technically in parallel because this is orange and this is blue on this side, and I have a green spot in the middle. So this pair, R2 and R3, are in parallel with R4. So I have to combine 2 and 3 in series before they're in parallel with resistor 4. All right, so now let's talk about Kirchhoff's rules. This is the real meat of this video and of basic circuits. These two rules help us understand almost all of what's going on in the circuit. So the two rules are foundational to physics: conservation of charge and conservation of energy. Now, as they apply to circuits, conservation of charge means that whenever we hit a junction and the current splits, the current that leaves the junction is the same as the current that enters the junction. Currents coming into the junction are positive, currents leaving the junction are negative. So when we add them all together, they should add to 0. Conservation of energy is a little bit more esoteric, if you will. As you go around a loop, any closed loop inside the circuit, the amount of volts that are supplied input into the circuit have to equal the voltage drops or the volts that are consumed as we go around. So we have to start at a spot and then go around and add up all the pluses and all the minus delta V's, and it should add up to 0. Here's a series circuit, and you can see in this one that the junction rule is real simple because there's only one current. But the conservation of energy, or the loop rule, we have quite a bit going on here. So let's go and take a look at it. So junction rule is super easy. So I put a junction right here, current 1 comes in, current 1 goes out. No big deal. That means the current has to be the same. But the loop rule, as we go around, I'm going to start here at the low end and go in the direction of the current. So I'm going to have a plus EMF as I go through the battery right here. And then I'm going to have a minus delta V going through resistor 1, 2, 3, and 4. So there it is written out. Now, remember, delta V equals I times R. So I1 R1, I1 R2, so forth and so on. Since the current is the same for each one, I can factor it out, and look what I get. I get this idea that the resistors in series all add up to be the total. So, current is constant in series, the resistors in series all add up, and the voltage drops add up to equal the total voltage supplied in the circuit. That's what Kirchhoff rules tell us about series. When you're on the test, please reference Kirchhoff's rules and try to avoid the words series and parallel as much as possible. Instead of series, say one pathway. Instead of parallel, say these two components have the same potential difference. All right, so now let's take a look at parallel. Let's apply conservation of charge and conservation of energy to a parallel circuit. So what do we get? The junction rule this time has a little bit more in play. So what we see is that at this junction, I would have a positive I3 and a negative I1 and I2. Or if you rearrange it, I1 and I2 have to equal I3. Now, in conservation of energy, in the loop, I have two separate loops. So if I go through this inner loop right here, I have a plus EMF and a minus IR for resistor 2, and I'm back where I began. That's this one. And for the second one, I have a EMF and a negative IR for resistor 1, okay? And when I add those two together, they should add up to 0. Now, since the volts are the same for both of these, we can see this. Up here, we can factor that out, and we can see that resistors in parallel add up as reciprocals. So, what do we learn from Kirchhoff's rules here? the sum of the individual currents add up to be the total that's supplied. And we've learned that the resistors add up as reciprocals. And we've also learned that the potential difference across everything in parallel is the same. Excellent. What about a combination circuit? So now we're going to put these rules in play for combo. So what do we get? So at this junction right here, we can see that I1 minus I2 and I3 must equal 0. And we can see that I2 and 3 positive coming into this junction equals a negative I4. Well, if you rearrange that, you can see that I1 and I3 have to be the same. I'm sorry, I1 and I4 have to be the same, which we could see already. In conservation of energy, we have two loops again. We have this inner loop and we have the outer loop. So the inner loop shows an EMF positive right here. Then we have an IR drop, I1, R1 for the first resistor, and then an I2, R2 for the second resistor, and an I2, R3 for the third resistor. Notice that I could factor the I out, and these two resistors add up, which we already know because they're in series. If we go around the outer loop, we can see that it's EMF I1, R1 minus, in this case, I3, R4, and that must add up to 0. All right, now that's a lot of stuff really quickly, and it's a lot of stuff to keep track of. So one of the tools that we use is a VIR or VIRP chart to keep track of all of our numbers. So if we have a circuit with all of these numbers right here, then if you write the component down, each one over here, and then total up the circuit as a whole, if you reduce the circuit down to just one resistor, one equivalent resistor, you would have 12 volts for the entire thing. So I would like for you to pause the video, fill in this chart, and then I'll show you the answers and see how you did. Pause the video.
All right, so let's solve this one. So right here we can first see that these two are in series. So 8 plus 4, that's 12 ohms. And then once we get there, we can see that the 12 and the 6 are in parallel. So I need my calculator for this one. 1 over 12 plus 1 over 6. Inverse, that's 4. This would be 4 ohms. And then this 4 ohm section and this 4 ohm together give us 8 ohms total for the entire thing. 8 ohms. All right, so now once we know that, we can figure out the current and the power. So remember, V equals I times R, so 12 divided by 8 gives us 1.5 amps right here, and the power would be that times 12, and I get 18 watts. All right, excellent. So now, let's go backwards. What has to be the same in any part of this? Well, we can see that the current that comes through here to here to here has to be the same. So this 4 ohm resistor right here, which is my 4 ohm resistor on the right, has to have 1.5 amps as well. And knowing that, I can figure out the volts, so that would be 6 volts here. So that's 6 volts for this one. That leaves, what, 6 volts left, because this is consuming 6, this is providing 12, so I have 6 volts left. And if we go around this loop right here, we can see that that's plus 12 minus something minus 6. So this has got to be 6 volts for this one. And since it's a 1 ohm resistor, that's 1 amp. All right, and now we can see that this has to have 1 amp here, and this around here has to have what's left. This was 1.5 amp, so that means going through these two must be 0.5 amps each. And then we can multiply these two, so that would be 2 volts here, and that would be 4 volts here, which makes total sense because the voltage across these two has to equal this one. This is 6 volts, and so that is, what do we get? 4 for this one and 2 for that one, which is 6. All right, and then we can just fill out the power by multiplying these together. This is 6 watts. This is, what is that, 1 watt. This is 2 watts. And this would be 9 watts. And so these should all add up to this. So 9, 10, 11, 12, and 18. So that's perfect. So we solved it. Awesome.
All right. You can also use VIRP charts for symbols. Now this is a little harder, but on the AP test, a lot of times they don't give you numbers. So you have to learn how to do this with symbols alone. So what I'd like for you to do, please pause the video, fill in this chart with the symbols. Excuse me, let's assume R1, R2, R3, and R4 are all the same resistance. Just make it R, all right? I just have them numbered so you know which one is which. They're all R right here. and the potential down here will be V. Now pause the video, see if you can fill in everything else. Pause the video.
Let's solve this one. Now, since this one's all symbols, I'm going to come the long way so you get a better idea what's going on. So all of these are just resistor R, and these two are in series, so those are going to end up being, when added up, 2R, and that's R, and then I have R over here, and there's my volts. Okay, so now I have these two that are in parallel, so I'm going to connect those two together, and when I do that, this one becomes, what did I get for that? 2/3 R, because I have to add 1 over 2R plus 1 over R equals 1 over the resistance in parallel. So I have to find a common denominator. When I add those together, that's 3 over 2R equals 1 over the resistance in parallel. So the resistance in parallel is 2R over 3, which is what I have here. Now, these two are in series, so I can just add them directly up, and I'm left with this, V. And then this one is going to be 2/3 plus 3/3, so I get 5/3 R. So that's my total, 5/3 R. So I know what the total volts are. That's V, that's given. So from these two, I can find I. So remember that I equals delta V over R, and for us, that's V over 5/3 R, which gives us 3/5 V over R. Now, you can tell that this is series, so the current that comes through here equals the current that goes through here. So that's our R1, so this would be 3/5 V over R as well, so they're the same. And now from these two, I can find the voltage across this, what this voltmeter right here would read. And so that's just those two multiplied, and so I get 3/5 V. Now, if this one is 3/5 V, and this is V, that means I have 2/5 left for over here. So that means this section over here has 2/5 volts across it. That means this section over here, because this was parallel, this also has to have 2/5 volts. So this resistor is resistor 2, that's 2/5 volts there. And from those two, I can find the current that goes through it. And the current equals V divided by R, so that would be 2/5 V divided by R. Okay? All right, now, we know that the current, actually this section has the same volts as this section, right? But they're in series. So I have to find the current that goes through here. So how am I going to do that? Well, the current that comes through here was 3/5 V over R. And the current that goes through this one over here is going to be, what was that? That was 2/5 V over R. So that's going to leave me with, this has to be 1/5 V over R. So these two up here are going to get 1/5 V over R. So that's 1/5 V over R, and that has to be 1/5 V over R. And then when I multiply these together, I get 1/5 V, and I get 1/5 V. Now see if that makes sense. The potential difference across these two has to be the same as this, because this sets in parallel with this. So the potential difference across R2 is 2/5, and this is 1/5 and 1/5, so that adds up. Let's check our current. The current that comes through here is the total, 3/5 V over R, and so these two currents that come here and here must be 2/5 plus 1/5, which is 3/5, so that adds up. All right, so now to find our power, all we have to do is multiply these out, and when I do, I'm going to get 9V squared over 25R. For this one, it's just P equals IV, and then this one will be 4/25 V squared over R, and this one is going to be, what is that, V squared over 25R, and this will be the same, V squared over 25R, and this one, when I multiply those two together, it's going to give me 3/5 V over R. And V's should all add up to be this one, so let's check. So they're all V, oops, sorry, that's a square. V squared over R, and that's 9/25, 4 more, and 1 and 1. So 9, 10, 11, 12, 13, 14, 15 over 25, which indeed is 3/5 V squared over R, so it all works out, and everything is right. Excellent.
All right, here's our answer. If you go through this in symbol form only, this is the answers you should get. All right, that's it. That is the basics of circuits. I hope that's helped you a lot. In our next video, we're going to do a little bit more advanced stuff like internal resistance of batteries and the brightness of bulbs and all of that sort of thing. All right, see you then. Bye.